Now see here root mean square value of AC here. So suppose if you have taken a circuit having resistance R and it is connected to AC source. When it is connected to AC source, current is passed through this and heat is generated across this resistor. So just you note down the value of the heat generated in one cycle by the AC and then you allow to pass a steady value of current through this circuit, and I will just write down the value of the steady current required for generating the same heat in the same time interval as it was produced by AC. So that steady value of current is known as root mean square value of AC here. So for calculation of the root mean square value of AC, we have to use here heating effect of AC here. So now see, suppose you have taken the instantaneous value of current, that is I is equal to I naught sin omega t. When it is passed through the circuit of resistance R, then heat generated at any instant dt is here I square R dt, this one. Put the value of I naught, I here, our dH is equal to I naught square sin square omega t R dt. So this is the heat generated by AC in time interval dt. So now we can calculate the heat generated by AC in one time in one cycle. So that we can write dH is equal to I naught square R is constant, can be taken outside, sin square omega t dt 0 to t here. So we can write H is equal to I naught square R, and that can be written 0 to t and 1 minus cos 2 omega t upon 2, that is your dt. We can write H is equal to I naught square R and can be written here 0 to t 1 dt minus here, and this 2 we can take outside. So here cos 2 omega t dt, that is 0 to t. When you integrate cos 2 omega t here, or you can say the average value of cos 2 omega t is equal to 0. So integration of this term is 0. So we can write this equation again here. So now this equation can be written as H is equal to I naught square R by 2 into T, that is the integration of this term. So this is the heat generated by AC in one cycle when it is passed through the resistance R. Now we can write the, if I RMS or IV here we take, is the steady value of current, is the steady value of AC, then heat produced in time interval T is, we can write H is equal to here I RMS square into R into T. So this is the heat produced by a steady value of current in time interval T when it is passed through the resistance R. You can equate these two, you will be getting I RMS square RT is equal to I naught square R by 2 into T. So this and this will get cancelled everything. You will be getting I RMS square is equal to I naught square by 2, that is I RMS is equal to I naught upon root 2. So this is the RMS value of AC, that means the root mean square value of AC, that is 1 upon root 2 times the peak value of AC, that is the maximum value of AC. And similarly we can calculate also here E RMS is equal to, that is E naught upon root 2, and also we can write V RMS, sometimes it is written the potential difference. So V RMS is equal to V naught upon root 2. So whether you write E RMS or V RMS, that is the same thing is here, and I RMS here. So in all these cases peak value of AC here, suppose if you are writing I naught, that is I RMS into under root of 2, that is the root 2 times of the RMS value. So, that is not RMS, that is a peak value. So, V naught is equal to V RMS into root 2. So, the peak value of voltage or peak value of current is more than the RMS value of current or the voltage. Now, see here, whatever the domestic supply is here, you say that is around the 220 volt, that means that is RMS value of the voltage. Similarly, if the current is flowing suppose 3 ampere or the 4 ampere, that is RMS value of current. Then you will have to calculate the peak value by using this formula. So, while solving the numerical, you have to take care of whether the RMS value is given to you or the peak value is given to you. Generally, when they say the current is flowing through the circuit or EMF is applied or the potential difference is applied or the supplied, that is generally here taken RMS value.